Hello, and welcome to Space Historians. I'm glad you've joined me, ready to slow down, breathe deeply, and let your thoughts drift weightlessly beyond our world. This is your moment to leave the noise of the day behind and step quietly into the vast, star-lit corridors of cosmic history. Each episode here isn't just about stars. It's about the stories they hold, the myths whispered by ancient astronomers, and the quiet mysteries still waiting. If you enjoy these quiet journeys, a like and a subscribe help keep this channel orbiting. But for now, you don't need to do anything but listen. Imagine this. Tonight, at this very moment, a beam of light leaves one edge of the Milky Way. It travels at the fastest speed in the universe, nearly 300,000 kilometers every second. It crosses distances that would take our fastest spacecraft millennia to traverse. It moves without pause, without slowing, without stopping. And yet, despite this incredible speed, that beam of light will not reach the other side of our galaxy for 100,000 years. If that photon could carry a message, the reply would not arrive until long after every human civilization we know has risen, flourished, and faded into memory. The pyramids would be ancient relics of an ancient time. The cities we live in would be dust. The languages we speak would be unrecognizable. And still, that light would be traveling, crossing the silent vastness of the Milky Way, moving through star fields and nebulae, past worlds we will never see. This is the impossible beginning of understanding how big the Milky Way really is. Not in numbers, not in equations, but in time. In the time it takes for light itself, the fastest thing that exists, to cross from one side to the other. We live inside this structure. Every star you see at night, every constellation, every planet visible to the naked eye, they are all part of this one galaxy. And yet the scale of it defies comprehension. To say the Milky Way is large is to say nothing at all. To say it is vast is still inadequate. The Milky Way is so enormous that even describing its size requires us to abandon ordinary measures and reach for something beyond human experience. Consider the Sun. It is a star like any other, burning quietly in the Orion arm of the galaxy. From Earth, it appears as the brightest object in the sky, the source of all warmth and light. But from the galactic center, 26,000 light-years away, the Sun is invisible. It is one faint dot among hundreds of billions, too small to matter, too distant to notice. And the galactic center itself, with its crowded core and supermassive black hole, is only halfway across the galaxy. There are stars in the Milky Way that are farther from us than we are from the center. There are regions of the galaxy so remote that no light from Earth has ever reached them. There are spiral arms we cannot see, hidden behind curtains of dust. There are clusters of stars older than the Sun, orbiting in the halo, far above and below the disk. The Milky Way is not one thing. It is a collection of regions, each with its own character, its own population, its own story. And yet we are inside it. We cannot see the full spiral from above. We are trapped within, like someone trying to measure the size of a forest while standing in the middle of it. Every observation we make is limited by our position. Every map we draw is incomplete. And still, we try. We count stars, measure distances, trace motions. We build models and simulations. We piece together a picture of something we can never see whole. The Milky Way is not just big in space. It is big in time. It has existed for more than 13 billion years, formed in the aftermath of the Big Bang when the first clouds of hydrogen collapsed under gravity. It has grown over eons, consuming smaller galaxies, pulling in streams of stars, shaping itself through collisions and mergers. What we see tonight is only one moment in a long history. The galaxy was different a billion years ago. It will be different a billion years from now. To ask how big the Milky Way is, then, is to ask many questions at once. How wide is it? How thick? How far does its halo extend? How much of it is visible, and how much is dark matter, invisible but real? How many stars does it contain? How many planets? How many worlds where life might exist? These are not simple questions. They do not have simple answers. And yet, the search for those answers has shaped our understanding of the universe itself. The Milky Way is our home, the only galaxy we can study from within. Everything we learn about it teaches us something about galaxies everywhere. Every measurement refines our sense of scale. Every discovery expands the boundaries of what we thought possible. Tonight, as you listen, you are inside the Milky Way. You are moving with it, orbiting the galactic center at hundreds of kilometers per second, though you feel nothing. The ground beneath you seems still. The stars above seem fixed. But in truth, you are part of a vast cosmic dance, a slow rotation that takes 225 million years to complete. You are not standing still. You are traveling through space, carried along by the galaxy itself. And somewhere, on the far side of that galaxy, a beam of light is moving toward us. It left 100,000 years ago, long before humans existed in their current form. It has crossed unimaginable distances, threading through star systems and dust clouds. And tonight, it arrives. It reaches your eye as a faint glimmer, one photon among trillions. And in that instant, you see the Milky Way not as it is now, but as it was in the deep past. This is the impossible beginning. The realization that the galaxy is so large that time and distance blur together, that to measure it is to confront the limits of comprehension, that to live within it is to be surrounded by more than we can ever know. 2,500 years ago, in the heart of ancient Babylonia, astronomers stood beneath the night sky and looked up. They did not know they lived inside a galaxy. They did not know what a galaxy was, but they saw the stars, countless and scattered, and they tried to make sense of them. The Babylonians were record keepers. They tracked the movements of planets, noted eclipses, charted the phases of the moon. They divided the sky into constellations, assigning names and stories to patterns they saw overhead. The stars were not random to them. They were signs, omens, markers of time and season. To study the heavens was to study the will of the gods, but among all the stars, one feature puzzled them. A faint band of light stretched across the night, pale and ghostly, like a river of mist. It did not move like the planets. It did not change like the moon. It was simply there, permanent and unchanging, arcing from horizon to horizon. The Babylonians called it the Heavenly River. Other cultures had different names. The Greeks imagined it as spilled milk from the breast of a goddess. The Chinese saw it as a silver stream separating lovers. The Inca believed it was the spine of the cosmos. Every civilization that looked up saw the same band of light and tried to explain it. What they did not know, what no one could know, was that they were looking at the Milky Way from the inside. That pale glow was not a river or a cloud. It was the combined light of billions of stars, too distant and too faint to see individually. It was the cross-section of a galactic disk, stretching outward in all directions, with Earth embedded somewhere within. The ancient astronomers did their best with the tools they had. They counted the brightest stars, catalogued their positions, mapped their movements across the seasons. Hipparchus, working in the 2nd century before the Common Era, created one of the first star catalogues, listing over 1,000 stars by position and brightness. Ptolemy expanded on this work, compiling the Almagest, a comprehensive guide to the heavens that would influence astronomy for over a millennium. But neither Hipparchus nor Ptolemy understood the Milky Way. To them, it was a curiosity, a feature of the sky with no clear explanation. Aristotle, writing centuries earlier, thought it might be an atmospheric phenomenon, something like a cloud or a meteor trail. He imagined vapours rising from the earth and catching fire in the upper air, creating the glow. It was a reasonable guess for someone without telescopes or modern physics, but it was wrong. For thousands of years, this misunderstanding persisted. The Milky Way remained a mystery, visible to everyone but understood by no one. It was there every clear night, unchanging, silent, offering no clues to its true nature. People lived their entire lives beneath it without knowing they were inside. Something vast, something that contained not just the stars they could see, but hundreds of billions more. The setting of this story is important. Ancient Babylonia, Greece, China, the Inca Empire. These were places where the night sky was dark and clear, unspoiled by artificial light. The Milky Way was not a faint smudge, glimpsed on rare occasions. It was a dominant feature of the heavens, impossible to ignore. It shaped their myths and guided their calendars. Imagine standing in a Babylonian city at night. The air is warm, the streets are quiet. Above, the sky is crowded with stars, more than most modern people have ever seen, and cutting across them all is the Milky Way, glowing softly, a river of light that seems to hold the heavens together. You do not know what it is. You cannot measure it, but you feel its presence. It is part of your world, as familiar as the sun or the moon. This is where the story of understanding the Milky Way begins. Not with telescopes or equations, but with simple observation, with the recognition that the sky holds patterns, that those patterns repeat, and that behind them lies something larger than individual stars. The Babylonians did not solve the mystery, neither did the Greeks or the Chinese, but they laid the groundwork. They showed that the heavens could be studied, that they followed rules, that they could be mapped and predicted. They turned the sky from a realm of gods and myths into a subject of inquiry, and in doing so, they planted the seeds of a question that would take millennia to answer. What is that band of light? Why does it stretch across the sky? Is it close or far away? Is it part of the earth or something beyond? These questions did not have answers in ancient times, but they were asked. And in the asking, the first steps were taken toward understanding the true size of the Milky Way. The human element here is crucial. The astronomers of Babylonia and Greece were not abstract thinkers detached from the world. They were people, living in cities, raising families, navigating the challenges of daily life. And yet, they looked up. They took time to wonder. They recorded what they saw and passed it on to the next generation. This continuity matters. The knowledge built slowly, across centuries, each generation adding a little more. The Babylonians charted the planets. The Greeks refined the measurements. The Islamic scholars preserved and expanded the work during the Middle Ages. The Renaissance astronomers built on all of it. The Milky Way, unchanging in the sky, became a thread connecting all these efforts. And through it all, no one knew they were inside it. No one suspected that the faint glow overhead was the edge of a structure so vast that crossing it would take light itself 100,000 years. They saw only the surface, the visible band, and tried to understand it with the tools they had. Cities, under dark skies, with patient observers who looked up and asked questions. And that journey, slow and winding, would eventually lead to the realization that the Milky Way is not just a feature of the sky, but the galaxy itself, our home among the stars. 1609, the year the heavens changed. Galileo Galilei, working in Padua, had heard rumours of a device from the Netherlands, a tube with lenses that could make distant objects appear closer. It was called a spyglass, used by sailors to spot ships on the horizon. Galileo, always curious, built his own version. He improved the design, increasing the magnification, refining the optics, and then, on a clear night, he pointed it at the sky. What he saw altered everything. The moon, which had always appeared as a smooth, perfect disk, revealed itself as a rugged world. Mountains cast shadows across its surface. Craters pocked its face. It was not a flawless, celestial sphere, but a place, a terrain, a landscape. Jupiter, which had seemed like a bright wandering star, showed itself as a sphere with 4 smaller points of light orbiting it. Moons. Other worlds circling a distant planet. And then Galileo turned his telescope toward the Milky Way. The pale band of light that had puzzled humanity for millennia dissolved before his eyes. What had seemed like mist, like a cloud, like a glowing vapor, was revealed to be stars. Not dozens, not hundreds, thousands upon thousands, packed so tightly that they blurred together when seen with the naked eye. The Milky Way was not a singular thing. It was a multitude. Galileo described it in his writings. He called it a congeries of innumerable stars, a gathering beyond counting. Where the eye saw only a faint glow, the telescope revealed a field crowded with light. Each point was a sun, perhaps like our own, scattered across distances too great to comprehend. This was the spark of mystery. The moment when the Milky Way shifted from myth to observation, from symbol to structure. It was no longer just a story told by ancient cultures. It was a physical phenomenon, something that could be studied, measured, understood. The implications were staggering. If the Milky Way was made of stars, how many were there? How far away were they? Were they all part of one system, or did the galaxy extend indefinitely? And what did it mean for humanity's place in the cosmos? Galileo did not answer these questions. His telescope was crude by modern standards, with a narrow field of view and limited magnification. But it opened the door. It showed that the universe was far larger, far more complex than anyone had imagined. The smooth celestial spheres of ancient philosophy were replaced by a universe filled with worlds, with moons, with countless suns. The discovery spread quickly. Other astronomers built telescopes and confirmed Galileo's observations. The Milky Way was indeed made of stars. The mystery deepened. If these were stars, why were they clustered in a band? Why did they appear brighter in some directions than others? What was the structure that held them together? For the first time, people began to think of the Milky Way not as a decoration in the sky, but as a system, a vast collection of stars, arranged in some pattern, bound together by forces unknown. It was the beginning of galactic astronomy. Though the term galaxy would not be used for centuries, Galileo's telescope also revealed something else. The universe was not static. It was not a perfect, unchanging creation. It was dynamic, varied, filled with structures that demanded explanation. The smooth heavens of Aristotle gave way to a cosmos that was rough, diverse, and full of surprises. This shift in perspective was profound. For thousands of years, the heavens had been seen as perfect and divine, beyond human understanding. Now, they were becoming a subject of study. The telescope brought the distant close. It turned the unreachable into the observable, and in doing so, it transformed astronomy from a philosophical exercise into an empirical science. The spark of mystery was not just the discovery of stars in the Milky Way. It was the realization that the universe could be known, that mysteries could be solved, that what seemed impossible to understand might, with the right tools, reveal its secrets. Galileo himself faced challenges. His discoveries threatened established beliefs. The idea that the moon had mountains, that Jupiter had moons, that the Milky Way was made of stars, these observations contradicted the teachings of the Church and the ancient philosophers. Galileo was eventually forced to recant some of his claims, placed under house arrest for the rest of his life. But the truth he uncovered could not be suppressed. The telescope had shown what was there. Others would see it too. And so the spark of mystery spread. Across Europe, astronomers began to explore the night sky with telescopes. They mapped the moon, tracked the planets, counted the stars. The Milky Way became a subject of intense interest. If it was made of stars, how many? And how were they distributed? The questions multiplied. Each answer led to new mysteries. The Milky Way was not uniform. It was brighter in some directions, dimmer in others. Dark patches interrupted the glow, regions where no stars seemed to shine. Were these voids, or was something blocking the light? Galileo's discovery was the beginning, not the end. It revealed that the Milky Way was far more complex than anyone had suspected. It was not just a band of light. It was a structure, a system, something that demanded deeper investigation. And in revealing this, Galileo changed not just astronomy, but the way humanity thought about itself. The universe was no longer a small, tidy creation with Earth at the center. It was vast, filled with stars beyond counting, stretching outward in all directions. The Milky Way was not the edge of creation. It was a feature within it. This was the spark, the moment when the mystery ignited, when the faint glow overhead became a question worth asking, when the invisible became visible, when the journey to understand the size of the Milky Way truly began. The world did not react quietly to Galileo's discoveries. When word spread that the Milky Way was not a cloud or a mist, but a field of countless stars, the response was mixed. Some were awed, others were skeptical. Many refused to believe it at all. The idea that what appeared as a faint glow could contain thousands of individual suns was difficult to accept. It challenged common sense. It contradicted centuries of teaching. For those who looked through telescopes themselves, the experience was transformative. To peer into the eyepiece and see the Milky Way dissolve into stars was to witness a revelation. What had seemed smooth and featureless became crowded and detailed. The heavens were not simple. They were complex beyond imagination. Imagine being one of the first to see it. You have spent your life looking up at the night sky, seeing the Milky Way as a familiar streak of light. Then, one night, you look through a telescope, and suddenly the streak is gone. In its place are stars. Hundreds of them, perhaps thousands, filling the field of view, shimmering against the black. Your mind struggles to reconcile what you see with what you have always believed. The universe expands before your eyes. This was the reaction of many who witnessed Galileo's discoveries firsthand. Awe, wonder, a sense that the cosmos was far larger, far stranger than anyone had imagined. The Milky Way was not a decoration, it was a population. And if it contained so many stars, what did that say about the size of the universe itself? But not everyone was convinced. Some refused to look through the telescope at all. They dismissed it as a trick, an illusion created by faulty lenses. How could a simple tube with glass change what was in the sky? Surely, what the eye saw unaided was more trustworthy. The telescope must be distorting reality, not revealing it. Others accepted that the telescope showed stars, but argued about what it meant. Were these stars part of the Milky Way, or were they somewhere else? Was the Milky Way a single structure, or a collection of many? The observations raised as many questions as they answered. Religious authorities were particularly troubled. The Church taught that the heavens were perfect, unchanging, created by God in a specific order. The idea that the moon had mountains, that Jupiter had moons, that the Milky Way was made of countless stars, these observations suggested a universe far more complex and less orderly than Scripture implied. If the heavens were not perfect, what did that mean for creation itself? Galileo's work was scrutinized, debated, and eventually condemned. The Inquisition demanded that he recant his support for the heliocentric model, the idea that Earth orbited the Sun. Though the Milky Way was not directly part of this conflict, his discoveries about it contributed to a broader sense of unease. The universe was changing, and not everyone wanted it to. But despite the resistance, the truth persisted. More astronomers built telescopes. More observations were made. The Milky Way's nature became harder to deny. Stars were there, visible to anyone who looked. The question shifted from whether the Milky Way was made of stars to why it appeared as a band, and what that structure meant. The awe felt by those who accepted the discovery was profound. To realize that the faint glow overhead was actually the light of thousands of suns was to grasp, even if only dimly, the scale of the cosmos. Each star might be like the sun. Each might have its own worlds. The possibilities were staggering. This sense of wonder spread through the scientific community. Astronomers began to think differently about the universe. It was not a small, enclosed space with Earth at the centre. It was vast, possibly infinite, filled with stars that stretched beyond the limits of vision. The Milky Way was a clue, a hint of the universe's true size. At the same time, the disbelief lingered. For ordinary people, the discovery made little practical difference. The stars still rose and set. The seasons still changed. Whether the Milky Way was a cloud or a collection of stars did not affect daily life. And so, for many, the old stories persisted. The Milky Way remained the river of the gods, the spilled milk, the backbone of night. But among scholars, the shift was irreversible. The telescope had shown something that could not be unseen. The Milky Way was made of stars. That fact became the foundation for all future work. The next step was to understand how those stars were arranged, how many there were, and what held them together. The reaction to Galileo's discovery was a mix of awe, disbelief, resistance, and acceptance. It reflected the difficulty of changing deeply held beliefs, the challenge of accepting new evidence, and the power of observation to reshape understanding. The Milky Way was no longer a mystery in the old sense, a symbol or a metaphor. It was a mystery in the new sense, a puzzle to be solved with tools and evidence. And as the dust settled, as the debates quieted, one thing became clear. The universe was far larger than humanity had ever imagined. The Milky Way, revealed as a field of stars, was only the beginning. The question now was not what it was, but how far it extended and what lay beyond. The discovery that the Milky Way was made of stars created a new problem. If it was a collection of suns, how many were there? And more importantly, did the Milky Way represent the entire universe, or was it just one part of something larger? This question divided astronomers for centuries. It was not a simple disagreement about measurements or observations. It was a fundamental debate about the nature, reality itself. Two worldviews clashed, each supported by evidence, each defended by brilliant minds. On one side were those who believed the Milky Way was the universe. Everything that existed, every star, every nebula, every structure in the night sky, was part of this one system. Beyond the Milky Way was nothing. The galaxy was all there was. This view made sense in many ways. The stars were clearly part of the Milky Way, visible as a band across the sky. The few fuzzy patches, the nebulae, seemed like clouds of gas within the same structure. There was no evidence, not yet, of anything beyond. That the universe contained countless galaxies, each like the Milky Way, scattered across unimaginable distances. This view was harder to prove. Telescopes could not yet resolve distant galaxies into stars. The evidence was indirect, based on patterns and probabilities, rather than direct observation. The debate came to be known as the Great Debate, though it was less a single event than a long, simmering disagreement that lasted from the 18th century into the 20th. At its heart was a paradox. The Milky Way was vast, filled with billions of stars. To suggest that it was only one of many seemed almost absurd. How could there be more than one universe? And yet, the alternative, that everything was contained within the Milky Way, seemed to make humanity central again, in a way that contradicted the lesson of Copernicus and Galileo. Science and mystery intertwined. The mystery was not supernatural, it was observational. What were those faint smudges seen through telescopes? Were they gas clouds within the Milky Way? Or were they distant galaxies? Without a way to measure their distance, the question could not be settled. Some astronomers tried to estimate the size of the Milky Way by counting stars. William Herschel, in the late 18th century, spent years systematically counting stars in different directions. He assumed that the farther you could see stars, the farther the galaxy extended in that direction. His maps suggested a flattened, disc-like structure with the sun near the center. This supported the idea that the Milky Way was everything. If we were near the middle, and the disk extended evenly in all directions, then the galaxy was likely the entire universe. But Herschel's method had a flaw. He did not account for interstellar dust, which blocks light and makes distant stars invisible. His maps showed the Milky Way as smaller than it really was, and they placed the sun in a central position it did not actually hold. The flaw was not known at the time, and so Herschel's work was accepted as the best available model. Others looked at the nebulae, those faint cloudy patches scattered across the sky. Some, like the Orion Nebula, could be resolved with better telescopes, revealing clusters of stars embedded in gas. These were clearly part of the Milky Way, but others, like the Andromeda Nebula, remained stubbornly fuzzy. No amount of magnification revealed individual stars. What were they? One camp argued they were gas clouds, or perhaps small clusters too distant to resolve. Another camp, following the philosopher Immanuel Kant, proposed that they were island universes, galaxies like the Milky Way, but far beyond its boundaries. Kant's idea was speculative, based more on philosophy than observation. But it planted a seed. The contradiction was sharp. If the Milky Way was the universe, then the nebulae had to be part of it. If the nebulae were distant galaxies, then the Milky Way was only one among many, and the universe was far larger than anyone had thought. Both views had support. Both had problems. Science works by resolving contradictions, but this one proved stubborn. For over a century, it persisted. Telescopes improved, but not enough to settle the question. Measurements were made, but they were inconclusive. The Milky Way remained a mystery, caught between two interpretations. The paradox exposed a deeper truth about science. Observation alone is not always enough. Interpretation matters. The same data can support different conclusions, depending on assumptions, and sometimes the only way forward is to wait for new tools, new methods, new evidence. In the meantime, the mystery deepened. If the Milky Way was the universe, why did it have such a specific shape? Why a disk and not a sphere? And if it was only one galaxy, why did the nebulae look so different from the star clusters within the Milky Way? These questions had no answers yet, but they kept astronomers searching, observing, thinking. The tension between science and mystery was not a failure. It was a sign that the question mattered, that the answer was important, and that the truth, whatever it was, would reshape humanity's understanding of the cosmos. The Milky Way stood at the center of this debate, both literally, in the old, model, and figuratively, as the test case for understanding the universe. Its size, its structure, its place in the cosmos, all of it hung in the balance. And the resolution, when it finally came, would not just answer the question. It would open a door to a universe far larger, far stranger than anyone had dared imagine. The question of the Milky Way's place in the universe created not just one debate, but many. Astronomers divided into camps, each with its own evidence, its own methods, its own vision of the cosmos. The divisions were not always hostile, but they were deep. To understand the Milky Way's size and structure meant taking a side, and the sides were not easily reconciled. One group believed in centrality. They argued that the sun was near the center of the Milky Way, which itself was the center of everything. This view had historical weight. For millennia, humanity had placed itself at the heart of creation. First, Earth at the center of the universe, then the sun at the center of the solar system. Now, perhaps, the sun at the center of the galaxy. It was a comfortable idea, one that preserved a sense of importance. William Herschel's work seemed to support this. His star count suggested a disc-shaped galaxy with the sun roughly in the middle. If you looked in all directions and saw similar numbers of stars, it stood to reason that you were centrally located. This interpretation fit the observations, at least superficially. and it aligned with a deep human desire to be at the center, to matter. Another group argued for periphery. They suspected that the sun was not central at all, but located somewhere in the outskirts of the galaxy. This view was less comforting. It suggested that humanity occupied no special place, that we were just another star in a vast system. But it explained certain observations better. The Milky Way appeared brighter in one direction, towards Sagittarius, and dimmer in others. If the sun were at the edge, looking inward, toward the center, this asymmetry made sense. Harlow Shapley, working in the early 20th century, became the champion of this view. He studied globular clusters, dense groups of stars that orbited the galaxy. By measuring their distances, he found that they formed a spherical halo, centered far from the sun. The conclusion was inescapable. The sun was not at the center of the Milky Way. It was tens of thousands of light years away, in the galactic suburbs. This was a profound shift. It meant that everything Herschel had assumed was wrong, not in method but in interpretation. The reason the sun seemed central in his maps was not because it was central, but because dust blocked his view of more distant stars. He was seeing only the local neighborhood, not the whole galaxy. Shapley's work caused division. Some accepted it immediately. The evidence was strong, the logic sound. Others resisted. It was hard to let go of the idea of centrality, even for scientists who prided themselves on objectivity. To admit that the sun was peripheral was to admit that humanity was peripheral, and that was not an easy step. At the same time, another division emerged over the nebulae. Were they part of the Milky Way, or separate galaxies? This question split the community as sharply as the debate over the sun's position. Heber Curtis argued that the spiral nebulae, like Andromeda, were island universes, separate galaxies far beyond the Milky Way. He pointed to their shapes, their spectra, and their apparent motion. They looked different from gas clouds. They looked like distant versions of the Milky Way itself. Shapley, ironically, disagreed. He believed the Milky Way was so large that the nebulae had to be part of it. If the galaxy was hundreds of thousands of light years across, as he thought, then the nebulae could easily fit within its boundaries. To suggest they were separate galaxies was to suggest a universe too large to be believed. This was the great debate of 1920. Held at the Smithsonian in Washington, Shapley and Curtis presented their cases. Shapley argued for a large Milky Way containing everything. Curtis argued for a smaller Milky Way surrounded by other galaxies. Neither could prove their case definitively. The evidence was not yet strong enough. The divisions were not just scientific. They reflected different philosophies, different temperaments. Some astronomers were comfortable with a vast universe, filled with countless galaxies. Others preferred a more contained cosmos, where the Milky Way was supreme. Some trusted models and calculations. Others trusted direct observation. Some were willing to speculate. Others demanded certainty. These divisions drove progress. Each side pushed the other to refine their arguments, to gather better data, to improve their methods. The competition was healthy, even when it was tense. It kept the question alive, kept astronomers working, kept the search for answers moving forward. But it also highlighted a deeper truth. The Milky Way was too large, too complex, to be understood from one perspective alone. Different methods revealed different truths. Star counts showed a disk. Globular clusters showed a halo. Nebulae hinted at structures beyond. Each piece of evidence added to the puzzle, but the full picture remained elusive. The division of minds was not a failure. It was a necessary stage. Science does not advance by consensus alone. It advances through disagreement, through testing, competing ideas, through the slow process of eliminating what is wrong and refining what is right. The debates over the Milky Way were part of this process. They forced astronomers to question assumptions, to seek better evidence, to think more carefully about what they were seeing, and in the end, the divisions would be resolved. Not by argument, but by observation. New tools would settle the questions that philosophy and logic could not. The Milky Way's size would be measured. Its position in the universe would be determined. The nebulae would be revealed for what they were. But that resolution was still years away. For now, the minds remained divided, each side certain, each side incomplete. William Herschel did not set out to map the entire Milky Way. He was a musician by training, a composer and oboist in Hanover, before moving to England. But when he turned his attention to astronomy, he brought with him a musician's patience and a craftsman's skill. He did not just use telescopes, he built them, and the telescopes he built were unlike anything the world had seen. His largest instrument, completed in 1789, had a mirror 40 inches across and a tube 40 feet long. It was a giant, requiring scaffolding to operate, assistants to move it, and clear, dark skies to make it worthwhile. Faint points of light, hidden from smaller instruments, became visible. Herschel could see deeper into space than anyone before him, and with that power, he began a project that would consume decades of his life. He would count the stars, all of them, or as many as he could. By surveying the sky in every direction, by tallying how many stars appeared in each region, he hoped to map the Milky Way's shape and size. The pursuit was methodical. Night after night, Herschel pointed his telescope at different sections of the sky. He counted stars in each field of view, recorded the numbers, and moved on. His sister Caroline assisted, keeping notes, managing the observations, ensuring nothing was missed. Together, they built a picture of the Milky Way, one patch of sky at a time. The work was tedious. Imagine standing outside for hours, peering through an eyepiece, counting faint points of light until your eyes ache, then doing it again the next night, and the night after that, for years. This was not glamorous science. It was labour, painstaking and slow. But Herschel was patient. He believed that careful observation, accumulated over time, would reveal the truth. His method was simple. If you could see more stars in one direction, that meant the Milky Way extended farther in that direction. If stars were sparse, the edge of the galaxy was near. By comparing star counts across the entire sky, you could infer the Milky Way's shape. The results suggested a disk. The Milky Way was flat, not spherical. It was wider than it was thick. Stars appeared roughly equal in all directions around the galactic plane, which implied that we were not at the edge, but somewhere in the middle. This conclusion felt right. It fit with the observations. It aligned with the idea that humanity occupied a special place, and it provided the first clear picture of the Milky Way's overall structure. For a time, it was accepted as truth. But Herschel's pursuit had limits. He could not account for what he could not see. Interstellar, dust, dark clouds of matter that absorb and scatter light, blocked his view of distant stars. In some directions, the Milky Way appeared to end, not because it actually ended, but because dust made it invisible. Herschel did not know about this dust. He counted what he could see and assumed that represented the whole. This was the flaw in his map. The Milky Way was larger than his count suggested, and the Sun was not central. But the flaw would not be discovered for over a century. In the meantime, Herschel's work stood as the best available model. The pursuit also revealed something else. The Milky Way was not uniform. Some regions were densely packed with stars. Others were sparse. Dark rifts cut through the band of light, areas where no stars seemed to shine. Were these true voids, or were they caused by something blocking the view? Herschel did not know, but he recorded them carefully. His work inspired others. Across Europe and later in America, astronomers built larger telescopes and conducted their own surveys. The pursuit of understanding the Milky Way became a shared project, a goal that transcended individual careers. Each generation added to the map, refining the picture, correcting errors, extending the boundaries. The pursuit was not without frustration. The Milky Way resisted easy measurement. Its structure was complex, its scale enormous. Every new observation seemed to raise more questions than it answered. How far did the disk extend? What lay beyond the visible stars? Were the dark rifts empty, or filled with something invisible? Herschel himself faced these questions but never fully answered them. His maps were incomplete, his conclusions partly wrong. But his pursuit was not a failure. He demonstrated that the Milky Way could be studied systematically, that its structure could be inferred from observation, that the task, though difficult, was not impossible. The pursuit continues even now. Modern astronomers use radio telescopes, infrared instruments, and space-based observatories to peer through the dust that blocked Herschel's view. They map the Milky Way in wavelengths he never imagined, revealing structures he could not see. The work is ongoing, the map still incomplete, but the spirit of the pursuit remains the same. Careful observation, patient accumulation of data, the belief that the Milky Way, vast though it is, can be understood. Herschel began this work with his giant telescopes and his meticulous star counts. Others continue it today using tools he could not have dreamed of. The pursuit is the same, the goal is the same, only the methods have changed. The star counts accumulated. Observation by observation, night by night, astronomers built a picture of the Milky Way. But the picture was incomplete, a mosaic with missing pieces. The clues were there, scattered across the sky, but they did not yet form a whole. One of the strongest clues was the shape. The Milky Way appeared as a band, not a sphere. This suggested a flattened structure, a disk rather than a ball. If stars were scattered evenly in 3 dimensions, the sky would look the same in all directions. But it did not. The concentration of stars along the galactic plane was undeniable. The Milky Way was flat. This clue pointed toward a disk-shaped galaxy, but it did not reveal the disk's size. How wide was it? How thick? How far from the center were we? These questions required more than just counting stars. They required measurements of distance. Distance is one of the hardest things to measure in astronomy. Stars do not come with labels indicating how far away they are. They appear as points of light, some bright, some dim. Brightness alone is not enough. A faint star could be close and intrinsically dim, or far away and intrinsically bright. Without knowing which, distance is impossible to determine. Astronomers developed methods. Parallax, the apparent shift of a star's position as Earth orbits the Sun, worked for nearby stars. By measuring this tiny shift, distances could be calculated, but parallax only worked for stars within a few hundred light-years. Beyond that, the shift was too small to detect. For more distant stars, other methods were needed. Variable stars, whose brightness changed in predictable patterns, became crucial. Cepheid variables, in particular, were discovered to have a relationship between their period of variation and their intrinsic brightness. If you knew the period, you could calculate the brightness, and from the brightness, the distance. These clues, fragments of data gathered from different methods, began to reveal the Milky Way's structure. The disk was about 100,000 light-years across, far larger than Herschel had estimated. The thickness was much less, only a few thousand light-years. The Sun was not at the center, but about halfway out, roughly 26,000 light-years from the core. But the data was messy. Different methods gave different answers. Some estimates placed the Milky Way at 50,000 light-years across. Others suggested 200,000. The uncertainty was large, the errors significant. The clues pointed in the right direction, but they did not yet converge on a single answer. Interstellar dust added to the confusion. Astronomers began to realize that the dark rifts in the Milky Way were not voids, but regions where dust blocked the light. This meant that many stars were hidden from view, invisible despite their presence. Star counts were incomplete, maps were distorted, the Milky Way was larger and more complex than it appeared. This clue, the discovery of dust was both frustrating and liberating. Frustrating because it meant much of the previous work was flawed. Liberating because it explained many of the puzzles. Why the Milky Way appeared brighter in some directions. Why certain regions seemed empty. Why distance measurements were inconsistent. Dust was the missing piece. The fragment that made the others fit together. Globular clusters provided another clue. These ancient, spherical groups of stars orbited the Milky Way in a halo, above and below the disk. By mapping their positions, Shapley inferred the location of the galactic center. It was not where the sun was. It was far away, in the direction of Sagittarius, hidden behind layers of dust. This fragment of evidence shifted the entire picture. If the galactic center was 26,000 light-years away, and the Milky Way extended roughly the same distance on the other side, then the galaxy was about 100,000 light-years across, maybe more. And the sun was not central. It was peripheral, tucked into a minor spiral arm, far from the crowded core. Each clue added to the understanding, but the fragments did not always agree. Some measurements suggested a smaller galaxy. Others suggested a larger one. Some placed the sun closer to the center. Others placed it farther out. The data was incomplete. The tools imperfect. The methods still evolving. But the process was working. Slowly, piece by piece, the Milky Way's structure emerged. The disk, the bulge, the halo, the spiral arms. Each region had its own character, its own population, its own history. The clues pointed toward a galaxy far larger and more complex than anyone had imagined a century before. The fragments also revealed something about the nature of science. Progress is not always smooth. Data does not always agree. Methods have flaws. But over time, with enough observations, enough corrections, enough refinement, the truth becomes clearer. The Milky Way did not reveal itself all at once. It revealed itself gradually, through the accumulation of clues and fragments, each adding a piece to the puzzle. And the puzzle was not yet complete. Even with the disk measured, the halo mapped, and the spiral arms traced, mysteries remained. How much of the Milky Way's mass was invisible? How did the spiral structure form? What lay at the very center? The clues provided answers, but they also raised new questions, each fragment pointing toward deeper layers of understanding. For most of human history, humanity imagined itself at the center. First, Earth was the center of the universe, with everything else revolving around it. Then, the sun became the center of the solar system, with Earth relegated to one of several planets. But even then, there remained a hope. Perhaps the sun was special. Perhaps it sat at the heart of the Milky Way, the grand focal point of all the stars. Shapley destroyed that hope. In the early 20th century, Shapley turned his attention to globular clusters. These ancient collections of stars, each containing hundreds of thousands or even millions of suns, orbited the Milky Way in a spherical halo. They were visible in telescopes, scattered across the sky, but no one had yet mapped their three-dimensional distribution. Shapley used Cepheid variable, stars to measure distances to the clusters. The method was painstaking. Each cluster required careful observation, tracking the brightness changes of individual stars, calculating periods, determining luminosities. The globular clusters were not distributed evenly around the sun. They clustered in one hemisphere of the sky, concentrated toward the constellation Sagittarius. If the clusters formed a spherical halo, and if they were concentrated in one direction, it meant only one thing. The center of that sphere was not near the sun, it was far away. Shapley calculated the distance. The center of the globular cluster system, which he assumed was also the center of the Milky Way, lay about 26,000 light-years away. The sun was not central. It was peripheral, located far out in the galactic suburbs. This was the hidden truth. For all of William Herschel's careful star counts, for all the assumptions of centrality, the sun was not at the heart of the Milky Way. It was off to one side, in a quiet region far from the crowded core. Humanity's place in the cosmos shrank once again. The realization was profound. It meant that the Milky Way was larger than anyone had thought. If the Sun was 26,000 light-years from the center, and the galaxy extended roughly the same distance on the other side, then the Milky Way was about 100,000 light-years across, possibly more. It was vast beyond comprehension. It also explained many puzzles. The Milky Way appeared brighter towards Sagittarius, because that was the direction of the galactic center, where stars were densest. It appeared dimmer in other directions because we were looking outward, toward the edge. The asymmetry was not a mystery. It was evidence of our offset position. Shapley's discovery faced resistance. To some, it seemed absurd. How could centuries of careful observation have missed something so fundamental? How could the Sun, the source of all life on Earth, the center of our solar system, be relegated to the outskirts of the galaxy? But the evidence was strong. The globular clusters did not lie. Their distribution pointed clearly toward a distant center. And as more data accumulated, the conclusion became inescapable. The Sun was not central. It was one star among billions, located in a minor spiral arm, far from the galactic heart. This hidden truth reshaped astronomy. It meant that maps of the Milky Way needed to be redrawn. The Sun's position had to be corrected. The galaxy's size had to be recalculated. Everything that had been assumed about our place in the cosmos had to be reconsidered. Shapley himself saw the broader implications. If the Sun was not central, then neither was Earth. Neither was humanity. We occupied no special position. We were not the focus of creation. We were simply here, in one small corner of a vast galaxy, looking out at a universe that did not revolve around us. This was humbling, but it was also liberating. To know our true place was to see the universe more clearly. To let go of centrality was to embrace a larger vision, one in which the Milky Way was not a small, tidy structure with us at its heart, but a vast, complex system in which we were one part among many. The hidden truth also opened new questions. If the Sun was 26,000 light-years from the center, what was at the center? What held the galaxy together? How did the spiral arms form? Why did globular clusters orbit in a halo? Each answer revealed new mysteries. Each layer of understanding exposed deeper layers of complexity. Shapley's work marked a turning point. Before him, astronomers had assumed centrality and built their models around it. After him, they knew better. The Sun was peripheral, the Milky Way was larger, and the universe, which had once seemed manageable, became almost incomprehensibly vast. The hidden truth was not just about distance. It was about perspective. It was about recognizing that what we see is shaped by where we stand, that our position in the galaxy limits our view, that to understand the whole, we must account for our own offset vantage point. This lesson extended beyond astronomy. It became a metaphor for knowledge itself. We are always observing from somewhere, never from nowhere. Our perspective is limited, shaped by our location, our tools, our assumptions. To uncover hidden truths, we must question what we take for granted, look beyond the obvious, and accept that the universe may not conform to our expectations. Shapley uncovered one such truth. The Sun is not central. The Milky Way is vast. And we, for all our aspirations, are residents of the galactic suburbs, looking inward at a center we cannot see, surrounded by a structure too large to fully comprehend. That is the hidden truth, and it changed everything. The question that divided astronomers for centuries finally had an answer, and the answer came from Edwin Hubble, working at the Mount Wilson Observatory in California in the early 1920s. Hubble had access to the most powerful telescope in the world at the time, the 100-inch Hooker telescope. With it, he could see farther and with greater clarity than anyone before him. He turned his attention to the Andromeda Nebula, one of the largest and brightest of the fuzzy patches scattered across the sky. For years, astronomers had debated what Andromeda was. Was it a gas cloud within the Milky Way, or a separate galaxy far beyond? No one could resolve individual stars within it, which kept the question open. But Hubble's telescope could. Night after night, he photographed Andromeda, capturing long exposures that revealed faint details invisible to the eye. And then, in one of those images, he found what he was looking for. A Cepheid variable star, its brightness changing in a regular pattern. By measuring the period of that variation, Hubble could calculate the star's intrinsic luminosity, and, from that, he could determine its distance. The calculation was straightforward. The star was far away, not thousands of light years, not tens of thousands, nearly 1,000,000 light years. Andromeda was not part of the Milky Way. It was a separate galaxy, an island universe, far beyond the boundaries of our own. This was the paradigm shift. The moment when the Milky Way stopped being the universe and became one galaxy among many. Hubble's discovery, published in 1924, settled the great debate. The nebulae were galaxies. The universe was vast beyond imagination. The Milky Way, enormous though it was only one small part of it. The implications were staggering. If Andromeda was a separate galaxy, then so were the other spiral nebulae. Each one was a collection of billions of stars, each one a structure comparable to the Milky Way. The universe was not a single galaxy. It was filled with them, scattered across distances that dwarfed even the Milky Way's size. Hubble's work did not stop there. He continued to measure distances to other galaxies, building a map of the cosmos that extended farther and farther. Each new measurement confirmed the same truth. The universe was larger than anyone had thought. Galaxies were everywhere, in every direction, stretching outward as far as telescopes could see. This shift in perspective was profound. It was not just a change in understanding. It was a change in worldview. The Milky Way, which had seemed like the entirety of creation, was revealed as one thread in a vast cosmic tapestry. To look up at the night sky was no longer to see the universe. It was to see one small corner of it. The paradigm shift also changed the way astronomers thought about the Milky Way itself. If other galaxies existed, then the Milky Way was not unique. Its structure, its spiral arms, its central bulge, these were features common to many galaxies. By studying others, astronomers could learn about our own. The Milky Way became both subject and comparison, both the galaxy we lived in and an example of a broader category. Hubble's discovery also resolved one of the longest-standing questions in astronomy. The universe was not small and enclosed. It was open, vast, possibly infinite. Galaxies filled it, each one a city of stars, each one separated from the others by immense distances. The Milky Way was no longer alone. This realization was humbling. Once again, humanity's place in the cosmos shrank. We were not at the center of the universe. We were not even at the center of our own galaxy. We were in the suburbs of the Milky Way, which itself was one of billions of galaxies. The scale was almost incomprehensible. But the shift was also exhilarating. To know that the universe was filled with galaxies was to know that the cosmos was richer, more complex, more full of possibilities than anyone had imagined. Each galaxy might contain billions of stars. Each star might have planets. Each planet might, just possibly, harbor life. The universe was not empty. It was teeming. The paradigm shift changed the questions astronomers asked. Before Hubble, the question was whether the Milky Way was the universe. After Hubble, the question was how many galaxies existed, how they were distributed, how they formed and evolved. The focus shifted from the Milky Way alone to the universe as a whole. But the Milky Way remained central to understanding. It was the galaxy we could study most closely, the one whose stars we could resolve, whose structure we could map, whose history we could trace. Everything learned about the Milky Way informed our understanding of other galaxies. And everything learned about other galaxies informed our understanding of the Milky Way. The paradigm shift was complete. The Milky Way was one galaxy among billions. The universe was vast, and humanity, for all its aspirations, occupied a small, peripheral position in one ordinary galaxy, in an ordinary part of the cosmos. This was the truth that Hubble revealed, and it changed everything. The realization came swiftly, but its effects unfolded slowly. Edwin Hubble's discovery that the Milky Way was just one galaxy among countless others did not merely change astronomy, it changed everything. The immediate ripple spread through science, philosophy, and culture, forcing humanity to reconsider its place in the cosmos once again. In the scientific community, the impact was profound. Astronomers who had spent decades arguing about whether the Milky Way was the universe suddenly had to reframe their entire field. Telescopes that had been used to map our galaxy now turned outward, searching for others. Research programs shifted. Funding priorities changed. The question was no longer what is the Milky Way, but what is the universe of galaxies? Textbooks had to be rewritten. The old cosmology, where the Milky Way represented everything, was obsolete. Students learning astronomy in the 1920s encountered a different universe than their teachers had known. The change was rapid, disorienting, and necessary. Science moves forward by discarding what is wrong, even when what is wrong was believed for generations. But the ripple extended beyond astronomy. Philosophers grappled with the implications. If the universe contained billions of galaxies, each with billions of stars, what did that mean for humanity? Were we significant at all? Could we claim any special status in such an incomprehensibly large cosmos? Some saw the discovery as confirmation of humanity's insignificance. We were not central, not special, not unique. We occupied one small planet around one ordinary star, in one unremarkable corner of one average galaxy among billions. From a cosmic perspective, we barely existed. This view was humbling, even nihilistic. If the universe was so vast, did anything we did matter? Others saw it differently. Yes, the universe was large. Yes, we were small. But we were also the ones who discovered this truth. Humanity might be tiny, but we had the capacity to understand the cosmos, to measure galaxies, to uncover the structure of reality itself. That was not insignificance. That was extraordinary. The fact that we could comprehend the universe, even from our peripheral position, made us remarkable. Artists and writers responded to the paradigm shift in their own ways. The Milky Way, which had inspired myths and metaphors for millennia, took on new meaning. It was no longer the edge of creation. It was one island in an ocean of galaxies. Poets wrote of cosmic loneliness, of humanity adrift in an infinite void. Others wrote of wonder, of the beauty of a universe so vast and so full of light. The cultural impact was subtle, but real. People who heard about Hubble's discovery, who read about it in newspapers or magazines, began to think differently about the night sky. The stars were not just decorations. They were part of structures, galaxies, systems that extended far, beyond what the eye could see. To look up was to look out into a universe of staggering complexity. Religious communities also grappled with the implications. If the universe was billions of galaxies large, what did that mean for creation, for humanity's relationship with the divine? Some saw the discovery as a challenge to faith, a sign that the cosmos was too vast, too impersonal to be governed by a caring creator. Others saw it as affirmation, evidence that creation was even grander, even more magnificent than Scripture had described. The immediate ripple was not just intellectual, it was emotional. To realize that the Milky Way was one among many was to confront a kind of cosmic loneliness. We were not at the center. We were not surrounded by familiar structures. We were in one galaxy, looking out at billions of others, each so distant that their light took millions of years to reach us. The universe was not cozy. It was vast and cold and indifferent. But there was also a sense of possibility. If galaxies filled the universe, then so did stars. And if stars filled the universe, then so did planets. The discovery of other galaxies implied the existence of countless worlds, some of which might be like Earth. For the first time, the question of life beyond our planet became not just philosophical, but practical. If the universe was so large, surely we were not alone. This question would take decades to explore, but it began with Hubble's discovery. The immediate ripple was the realization that we lived in a universe capable of containing other worlds, other possibilities, other forms of life. The Milky Way was not special, and if it was not special, then neither was Earth. And if neither was special, then perhaps life itself was not rare, but common. The ripple also affected how people thought about time. If galaxies were millions of light years away, then the light we saw from them left long before humans existed. To look at a distant galaxy was to look into the past. The universe was not just large in space, it was large in time. The Milky Way was part of a history that stretched back billions of years, to the formation of the first galaxies, to the Big Bang itself. This realization added depth to the cosmos. It was not a static picture, but a story. Galaxies formed, evolved, collided, merged. The universe was dynamic, always changing. The Milky Way had a past, a present, and a future. And that future would be shaped by its interactions with other galaxies, by the slow processes of cosmic evolution. The immediate ripple of Hubble's discovery was a shift in perspective. The Milky Way went from being the universe to being one small part of it. Humanity went from being central to being peripheral. The cosmos went from being comprehensible to being almost incomprehensibly vast. And yet, in the midst of this vastness, there was also beauty. The universe was filled with galaxies, each one a collection of light, each one a story waiting to be told. The ripple continued to spread, touching every aspect of how we thought about ourselves, our place, our future. It would reshape science, inspire art, challenge philosophy, and ultimately lead to a deeper understanding of the cosmos and our role within it. But all of that began with one simple realization. The Milky Way was not alone. Hubble's discovery did not fade. It echoed through time, reshaping not just the immediate understanding of the cosmos, but the trajectory of human thought for generations to come. The realization that the Milky Way was one galaxy among billions became a foundation upon which countless other discoveries were built. In the decades that followed, astronomy exploded. New telescopes revealed more galaxies, each one adding to the census. The universe went from containing a few dozen known galaxies to hundreds, then thousands, then millions. Today, estimates suggest there are 2 trillion galaxies in the observable universe, each one a vast collection of stars. The echo of Hubble's work reverberates in every one of these discoveries. The structure of the universe itself began to reveal itself. Galaxies were not scattered randomly. They clustered together, forming groups and superclusters, separated by vast voids. The Milky Way belonged to the local group, a collection that included Andromeda, Triangulum, and dozens of smaller galaxies. The local group, in turn, was part of the Virgo supercluster, a massive structure containing thousands of galaxies. This hierarchical structure, from individual galaxies to clusters to superclusters, showed that the universe was organized on scales even larger than Hubble had imagined. The echo of his discovery was the realization that structure existed at every level, that the cosmos was not chaos but order, shaped by gravity over billions of years. The echo also reached cosmology, the study of the universe as a whole. If galaxies existed in such numbers, then the universe itself must have a history. How did it begin? How did galaxies form? These questions led to the development of the Big Bang theory, the idea that the universe started as a hot, dense state and expanded over time, cooling and allowing matter to clump into stars and galaxies. The Milky Way, in this context, became a test case. By studying its age, its composition, its structure, astronomers could infer how galaxies in general formed and evolved. The globular clusters, with their ancient stars, told of a time when the Milky Way was young. The spiral arms, with their active star formation, told of ongoing processes. The history of the Milky Way was a window into the history of the universe itself. The echo reached even further, into the realm of philosophy. The idea that we lived in one galaxy among billions forced humanity to reconsider its significance. This question, already raised by Copernicus and Galileo, became even sharper. If Earth was not the centre of the solar system, and the Sun was not the centre of the galaxy, and the galaxy was not the centre of the universe, then what did that say about us? Some thinkers embraced the smallness. We were insignificant, they argued, and that was freeing. It meant that our troubles, our conflicts, our anxieties were tiny in the grand scheme. The universe did not care about us. We were free to find our own meaning, unburdened by cosmic importance. Others resisted this view. Yes, we were small, they said, but we were also conscious. We could observe the universe, understand it, appreciate its beauty. That made us significant, not despite our size, but because of our awareness. The echo of Hubble's discovery was not nihilism, but wonder. We were part of something vast, and we could comprehend it. In literature and art, the echo was profound. Science fiction writers imagined civilizations on planets in other galaxies. They explored themes of isolation, of the vast distances separating stars and galaxies, of the loneliness of intelligent life in an enormous cosmos. The Milky Way became a character in these stories, a home that was both familiar and impossibly large. Artists painted galaxies, inspired by the photographs coming from telescopes. The spiral arms, the glowing cores, the dark dust lanes, these became subjects of beauty. The echo of Hubble's discovery was aesthetic as well as intellectual. The universe was not just large, it was beautiful. The echo also shaped education. Generations of students grew up learning that the Milky Way was one galaxy among billions. This knowledge became foundational, a baseline for understanding the cosmos. Children looked up at the night sky and knew that the faint band of light was the edge of their galaxy, that beyond it lay countless others, invisible to the naked eye, but real. This shift in education had consequences. It fostered a sense of curiosity about the universe, a desire to explore beyond the familiar. It also fostered humility, an understanding that humanity did not occupy a central position. These lessons, subtle but powerful, shaped the way people thought about science, about knowledge, about their place in the world. The echo reached into politics and culture as well. The space race of the 20th century, the drive to send humans to the moon and probes to the planets, was fueled in part by the realization that the universe was vast and full of possibilities. If galaxies existed in such numbers, then surely humanity could venture beyond Earth, could explore the cosmos, could become a spacefaring species. The echo of Hubble's discovery is still heard today. Every new galaxy discovered, every deeper image captured by telescopes, every refinement of our understanding of the universe builds on the foundation he laid. The Milky Way is one galaxy among billions. That truth, simple and profound, continues to shape how we see ourselves and our place in the cosmos. And the echo will continue. Future generations will build even larger telescopes, see even farther into space, discover even more galaxies. They will refine our understanding of the Milky Way, measure its size more precisely, map its structure in greater detail. But the fundamental truth will remain. We live in one galaxy among many, part of a universe so vast that it defies complete comprehension. The echo through time is the legacy of discovery. Each generation builds on the last. Each answer leads to new questions. Each step forward reveals new horizons. Hubble's discovery was one such step, a moment when the universe expanded before our eyes. and the echo of that moment will reverberate as long as humans look up at the stars and wonder. Behind every great discovery lie the dreamers, the people who dared to ask questions no one else thought to ask, who spent lifetimes chasing answers that might never come. The story of understanding the Milky Way is not just a story of telescopes and equations. It is a story of people, of their obsessions, their frustrations, their moments of clarity. William Herschel was one such dreamer, a musician who became an astronomer not through formal training but through passion. He built his own telescopes because the ones available were not good enough. He spent nights counting stars because he believed that patience and persistence would reveal the truth. His sister Caroline worked beside him, recording observations, managing the instruments, contributing to the work in ways that history often overlooks. Together, they mapped the sky, driven by the belief that the Milky Way could be understood. Herschel's dream was incomplete. His maps were flawed, his conclusions partly wrong, but his dedication laid the groundwork. He showed that systematic observation, accumulated over years, could reveal patterns. He demonstrated that the Milky Way had a structure even if he could not see it fully. His legacy was not perfection, but method. Harlow Shapley was another dreamer, a farm boy from Missouri who studied at Princeton and eventually directed the Harvard College Observatory. Shapley was driven by a simple question: where was the center of the Milky Way? The question consumed him. He studied globular clusters, measured their distances, calculated their distribution. Night after night, he collected data, refined his models, pushed toward an answer. When he concluded that the sun was not central, that we lived in the galactic suburbs, he faced resistance. But Shapley was certain. The evidence was clear. He had followed it wherever it led, even when it challenged comfortable assumptions. His dream was truth, no matter how humbling. Shapley's work was not flawless. He overestimated the size of the Milky Way, thinking it was larger than it really was. He argued against the idea that nebulae were separate galaxies, a position that would be proven wrong. But his core insight, that the sun was peripheral, was correct, and that insight reshaped our understanding of the galaxy. Edwin Hubble was perhaps the most famous of the dreamers. A lawyer who left the profession to become an astronomer, Hubble had access to the best telescope in the world and used it to answer one of the oldest questions. Are we alone in the universe? Not in the sense of life, but in the sense of structure. Is the Milky Way the only galaxy, or are there others? Hubble's dream was to see farther, to resolve the fuzzy nebulae into stars, to measure distances that no one had measured before. He photographed Andromeda, searched for variable stars, calculated distances, and when the answer came, when Andromeda revealed itself as a separate galaxy, Hubble did not stop. He continued, measuring more galaxies, building a map of the universe that extended farther than anyone had thought possible. Hubble's legacy was the expansion of the cosmos itself. He showed that the universe was larger than the Milky Way, that galaxies filled the void, that structure extended in every direction. His dream became reality, and in becoming reality, it opened doors to new dreams, new questions, new frontiers. But the dreamers were not only the famous names. There were countless others, assistants, technicians, observers, people who spent nights at telescopes, who developed photographic plates, who performed calculations, who contributed in ways that did not earn headlines but were essential to the work. Caroline Herschel, Williamina Fleming, Henrietta Leavitt, women whose contributions were often overlooked but whose work was foundational. Henrietta Leavitt discovered the period luminosity relationship for Cepheid variables, the key to measuring cosmic distances. Without her work, Hubble could not have determined that Andromeda was a separate galaxy. Her dream was simpler, perhaps less grand. She wanted to understand variable stars. But in pursuing that dream, she gave astronomy a tool that would unlock the universe. These dreamers shared certain qualities: patience, because the work was slow; persistence, because the answers did not come easily; curiosity, because they cared about questions that had no immediate practical value, and a willingness to be wrong because science advances by correcting errors, by refining models, by accepting that today's truth may be tomorrow's approximation. The dreamers also shared sacrifices. Herschel gave up a comfortable career in music. Shapley worked in relative obscurity for years before his breakthrough. Hubble faced skepticism and competition. Leavitt worked without recognition during her lifetime, her contributions acknowledged only after her death. The dream of understanding the Milky Way demanded dedication, and those who pursued it paid the price. But the dreamers also experienced moments of clarity, moments when the pieces fit together, when the mystery yielded to understanding. Those moments made the sacrifices worthwhile. To see the Milky Way not as a mystery but as a structure, to measure its size, to place it in context. Among other galaxies, these were achievements that transcended individual lives. They became part of humanity's collective knowledge, gifts to future generations. The dreamers remind us that science is not impersonal. It is deeply human, driven by curiosity, passion, and the desire to know. The Milky Way did not reveal itself through abstract processes. It revealed itself through people, through their questions, their observations, their willingness to spend lifetimes chasing answers that might never come. And the dream continues. Today's astronomers, working with tools the early dreamers could not have imagined, carry on the work. They map the Milky Way in wavelengths beyond visible light. They trace dark matter, measure the galaxy's rotation, predict its future. They are the next generation of dreamers, building on the foundation laid by those who came before. The story of the Milky Way is their story, a story of human curiosity reaching toward the stars, of minds refusing to accept the limits of the visible, of the quiet persistence that turns mystery into knowledge. The dreamers made it possible, and their legacy is the universe we now understand. Not everyone accepted the new cosmology. Even after Edwin Hubble proved that other galaxies existed, even after Shapley showed that the Sun was not central, resistance remained. The battle for truth is never simple. New ideas, no matter how well supported, must fight for acceptance. The resistance came from several directions. Some astronomers genuinely disagreed with the evidence. They pointed to uncertainties in distance measurements, to errors in calculations, to alternative explanations that preserved the old models. Science thrives on skepticism, and healthy debate can sharpen understanding. But sometimes skepticism becomes stubbornness, and the battle turns personal. Shapley and Heber Curtis exemplified this tension. In the Great Debate of 1920, they presented opposing views about the nature of the universe. Shapley argued that the Milky Way was enormous, containing everything. Curtis argued that it was smaller, surrounded by other galaxies. Both had evidence, both had logic, but they could not both be right. The debate was not resolved that night. Neither side convinced the other. The audience left without a clear victor. Only later, when Hubble's observations provided definitive evidence, did the question settle. Shapley had been right about the Sun's peripheral position. Both had been partly correct, partly wrong. The battle ended not with one side defeating the other, but with new evidence making the old arguments obsolete. But even with Hubble's discovery, resistance persisted. Some astronomers refused to accept that the universe was so large. The idea of billions of galaxies, each millions of light years away, seemed absurd. How could the cosmos be that vast? How could humanity comprehend such scale? It was easier to doubt the measurements, to question the methods, than to accept the implications. This resistance was not irrational. Science depends on skepticism. Extraordinary claims require extraordinary evidence, and the claim that the universe contained billions of galaxies was extraordinary. The skeptics demanded better data, more precise measurements, independent confirmation. They were right to do so. Only through rigorous testing could the truth be established. The battle was also philosophical. To accept that the Milky Way was one galaxy among many was to accept a diminished place in the cosmos. For some, this was a step too far. They clung to the idea that humanity, Earth, the Sun, the Milky Way, held some special status. To let go of that was to confront a kind of cosmic insignificance. Religious thinkers faced similar struggles. If the universe was so vast, did that challenge the idea of divine creation? Did it make humanity less important to God? Some saw the new cosmology as a threat to faith. Others embraced it, arguing that a larger universe was a more magnificent creation. The battle was not just scientific. It was cultural, spiritual, existential. In universities and observatories, the battle played out in debates, in journal articles, in conferences. Established astronomers, invested in the old models, resisted change. Younger scientists, eager to embrace new ideas, pushed forward. The generational divide was real. Those who had built careers on one understanding of the cosmos were reluctant to abandon it. Those just entering the field had no such attachment. The battle also involved institutions. Funding agencies had to decide which projects to support. Observatories had to choose which questions to pursue. The shift from studying the Milky Way as the universe to studying it as one galaxy among many required reallocating resources, retraining staff, rethinking priorities. Institutional inertia slowed the process, but gradually the evidence accumulated. More galaxies were discovered, distance measurements improved. The structure of the universe became clearer. The battle for truth was won not by rhetoric, but by observation. The universe revealed itself, and those who looked closely could not deny what they saw. Even so, acceptance was not immediate or universal. Decades after Hubble's discovery, some astronomers still questioned details. How accurate were the distance measurements? How certain were we that Andromeda was truly a separate galaxy? Could there be alternative explanations? These questions were reasonable, even necessary, but over time, as the evidence strengthened, the doubts faded. The battle also left scars. Reputations were damaged, friendships ended, careers stalled. Those who clung too long to the old models found themselves sidelined, their work dismissed as outdated. Those who embraced the new too quickly sometimes made mistakes, overreaching beyond what the evidence supported. The path from mystery to understanding was not smooth. Yet the battle was necessary. Truth does not emerge from consensus alone. It emerges from conflict, from the clash of ideas, from the testing of hypotheses against evidence. The resistance to the new cosmology forced its proponents to be rigorous, to refine their measurements, to address objections. The final result was stronger because it had been challenged. The battle for truth about the Milky Way also set a precedent. It showed that science could overturn centuries of belief, that new tools could reveal new realities, that humanity's understanding of the cosmos was not fixed but evolving. This lesson would apply to future discoveries, to the expansion of the universe, to dark matter, to the Big Bang itself. Each new idea would face its own battle, its own resistance, its own eventual acceptance. And so the battle for truth about the Milky Way became part of a larger story. The story of how science works, how knowledge grows, how humanity slowly, painfully, but inevitably comes to understand the universe. The battle was difficult, but it was also necessary. And in the end, truth won. Something shifted in the human mind. Not all at once, not for everyone, but slowly, over decades, a new awareness took hold. We began to see ourselves differently, not as the center of creation, not as the focus of the cosmos, but as residents of a galaxy, citizens of the Milky Way, part of something vast and ancient. This awareness changed the way people thought about their place in the universe. Before, the stars were distant decorations, beautiful but separate. Now, they were neighbors, fellow members of the galaxy. The sun was not alone. It was one star among hundreds of billions, all bound together by gravity, all moving through space in a slow, coordinated dance. To understand that we lived inside a galaxy was to gain perspective. The problems of daily life, the struggles and conflicts, the triumphs and failures, all of it took place within a tiny corner of an enormous structure. The Milky Way did not care about human affairs. It existed on timescales far longer than civilizations, on distances far greater than continents. To see oneself as part of it was humbling. But the awareness was not only humbling, it was also empowering. To know that we lived in a galaxy, to understand its structure, to measure its size, these were achievements. Humanity had figured it out. We had used tools, observations, mathematics to uncover truths about something incomprehensibly large. That required intelligence, creativity, persistence. The awareness of our smallness was balanced by the awareness of our capability. The new awareness also fostered a sense of connection. Every person who ever lived, every civilization that rose and fell, every story ever told, all of it happened within the Milky Way. The galaxy was not just a structure in space. It was a context for history, a setting for the human story. To look up at the night sky and see the Milky Way was to see home, not just Earth, but the entire galactic system that held us. This sense of connection extended beyond humanity. The elements in our bodies, the carbon, oxygen, nitrogen, iron, were forged in stars that lived and died within the Milky Way. Supernovae scattered those elements across the galaxy, where they eventually gathered into the Sun and Earth. We were made of stardust, literally. The atoms in our hands had been inside stars billions of years ago. The Milky Way was not something we lived near. It was something we were made from. The awareness also changed how people thought about the future. If we lived in a galaxy, could we explore it? Could humanity travel to other stars, visit other worlds within the Milky Way? These questions moved from fantasy to possibility. The galaxy was vast, yes, but it was not infinite. It was bounded, measurable, conceivable. Perhaps one day we could venture beyond Earth, beyond the solar system, into the galaxy itself. This vision of a future among the stars inspired generations. Science fiction writers imagined civilizations spreading across the Milky Way, building colonies on distant planets, encountering other intelligent species. These stories reflected the new awareness, the realization that the galaxy was not just a backdrop but a frontier, a place full of possibilities. The awareness also brought a sense of responsibility. If the Milky Way was our home, then we were part of it, responsible to it in some way. The galaxy would endure far longer than humanity. Stars would continue to form and die. The spiral arms would continue to turn, long after we were gone. To be aware of this was to recognize our transience, to see ourselves as one brief moment in a long history. But the awareness was not fatalistic. Yes, we were temporary, but we were also conscious. We could observe the galaxy, appreciate its beauty, understand its workings. That made us significant, not in size, but in awareness. The Milky Way was vast and ancient, but it did not know itself. We did. We could look outward, map the stars, trace the spiral arms, imagine the structure whole. That act of understanding was itself meaningful. The new awareness also fostered curiosity. If the Milky Way was so large, what else was out there? Beyond the galaxy, what lay in the dark between galaxies? How did the Milky Way compare to others? What was the universe like on even larger scales? The awareness of the galaxy's size opened the door to questions about the cosmos itself. For individuals, the awareness could be personal and profound. To stand under the night sky, to see the Milky Way stretching overhead, and to know that you were inside it, that you were part of its structure, that your atoms came from its stars. This was a moment of connection. It was a way of feeling small and large at the same time. insignificant, and extraordinary. The awareness spread through education, through books, through planetarium shows, through conversations. Children grew up learning that they lived in a galaxy, that the Milky Way was their cosmic address. This knowledge became part of the foundation of understanding, a baseline for thinking about the universe, and as the awareness grew, so did a sense of unity. Humanity might be divided by borders, languages, beliefs, but we all lived in the same galaxy. We all orbited the same galactic center. We all looked up at the same stars. The Milky Way was a common home, a shared context, a unifying structure that transcended the divisions of Earth. The new awareness was not a destination but a beginning. To know that we lived in a galaxy was to open the door to deeper questions, to further exploration, to a richer understanding of the cosmos. It was a shift in perspective, from seeing ourselves as central to seeing ourselves as part of something larger. And that shift, subtle but profound, changed the way humanity thought about itself and its place among the stars. The Milky Way is 100,000 light-years across. That is the number most often given, the measurement most people remember. But it is not the whole truth. The deepest truth about the Milky Way's size is more complex, more layered, and far stranger than a single figure can capture. The 100,000 light-years refers to the visible disk, the flat spiral of stars and gas that forms the galaxy's most obvious feature. If you could hover above the Milky Way and look down, this is what you would see. A bright bulge at the center, spiral arms curving outward, star clusters and nebulae scattered throughout. From edge to edge, this structure spans roughly 100,000 light-years. But the disk is not the entire galaxy. Surrounding it is the halo, a spherical region filled with old stars and globular clusters. The halo is dimmer, less densely populated, years from the galactic center. That is 3 times the width of the disk. Already, the Milky Way is larger than the simple figure suggests. Yet even the halo is not the end. Beyond the visible stars, beyond the globular clusters, lies the dark matter halo. This invisible component outweighs everything we can see. It does not emit light, does not interact with electromagnetic radiation. We detect it only through its gravitational pull, through the way it shapes the motions of stars and gas. The dark matter halo extends far beyond the visible galaxy. Some models suggest it reaches 1 million light-years from the center, perhaps more. If this is true, then the Milky Way is 10 times larger than the disk, a vast sphere of invisible mass surrounding the glowing spiral we think of as the galaxy. This is the deepest truth. The Milky Way is not one size but many, depending on what you measure. The disk is 100,000 light-years. The stellar halo is 300,000. The dark matter halo is 1 million. Each figure is correct. Each captures a different layer of the galaxy, but none, alone, tells the full story. The realization that most of the Milky Way is invisible is profound. We live inside something we cannot see, held together by forces we cannot directly observe. The stars, the spiral arms, the bright regions of star formation, these are only the surface. The bulk of the galaxy is dark, hidden, known only through inference. This deepest truth also changes the way we think about the galaxy's mass. The visible stars contribute about 100 billion solar masses. The gas and dust add a bit more. But the dark matter, invisible though it is, contributes 5 to 10 times as much. The Milky Way weighs far more than it appears. Its true mass is dominated by something we do not yet understand. The nature of dark matter remains one of the greatest mysteries in physics. We know it must exist because the galaxy's rotation does not match what the visible mass would produce. Stars on the outer edges move too fast. Without dark matter, they would fly off into space. The galaxy's gravity would not be strong enough to hold them, but they do not fly off. They remain bound, orbiting steadily. Something invisible provides the extra gravity. The deepest truth also involves time. The Milky Way is not static. It is evolving, changing over billions of years. The disk we see today formed gradually, as gas fell into the galactic plane and coalesced into stars. The halo formed earlier, from the first generation of stars. The dark matter halo formed even earlier, in the first moments after the Big Bang, when matter began to clump together under gravity. Each layer, the disk, the halo, the dark matter, tells a story about when and how it formed. The deepest truth is not just about size in space, but about size in time. The galaxy is billions of years old, and every part of it carries the marks of that age. The deepest truth also includes motion. The Milky Way is not stationary. It moves through space, part of the local group, heading toward the Virgo supercluster. Its dark matter halo overlaps with Andromeda's, the two already connected by invisible threads of gravity. In a few billion years, they will merge. The Milky Way as we know it will cease to exist, transformed into something larger. This future merger redefines size. If the Milky Way and Andromeda are already gravitationally bound, if their halos are already overlapping, then where does one galaxy end and the other begin? The deepest truth is that galaxies are not isolated objects. They are part of larger structures, always interacting, always evolving. The deepest truth is also humbling. The Milky Way, vast as it is only one galaxy among billions. And even within the Milky Way, most of what exists is invisible to us. We live on a small planet, around a small star, in a small corner of the visible disk, surrounded by a dark halo we cannot see. The deepest truth is that we know very little, that the galaxy holds mysteries we have not yet begun to unravel. But the deepest truth is also inspiring. We have measured the Milky Way, traced its structure, inferred its mass. We have done this despite our limitations, despite our small size, despite the fact that we are inside and cannot see the whole. The deepest truth is that humanity, tiny though we are, can understand the galaxy. We can ask questions about its size and find answers. We can look at the invisible and deduce its presence. The Milky Way is 100,000 light years across, and it is 300,000, and it is 1,000,000. All of these are true. The deepest truth is that the galaxy is layered, complex, mostly invisible, always evolving. To measure it is to confront the limits of knowledge and to push beyond them. And in that pursuit, we find not just numbers, but meaning. What does it mean to live inside something so large you can never see it whole? This is not just a question about the Milky Way. It is a question about existence itself, about perspective, about the limits of human understanding and the reach of human imagination. To live in the Milky Way is to be surrounded by more than we can ever know. Every star you see at night is part of this galaxy, but for every star you see, there are millions you cannot. They are too faint, too distant, blocked by dust or simply beyond the reach of vision. The Milky Way is not what you see, it is what surrounds you, invisible but real, shaping your motion, your history, your very existence. This creates a strange paradox. We are part of the galaxy, deeply embedded in its structure, and yet we cannot perceive it fully. We see only fragments, only hints. The band of light across the sky is not the Milky Way. It is our view of it, a cross-section, a glimpse of something far larger. To live inside is to be both intimately connected and profoundly blind. What does that mean? Perhaps it means that knowledge is always partial. No matter how much we learn, no matter how many instruments we build, we will never see the Milky Way as an outsider would. We cannot step back, cannot hover above, cannot take the perfect photograph that shows it whole. Our perspective is limited by our position. And yet, we learn anyway. We infer, we measure, we model. We build a picture from fragments. This is a lesson not just about the galaxy, but about all understanding. We are always inside something, always limited by our vantage point, always piecing together a larger truth from incomplete evidence. The Milky Way teaches us that this is not a failure. It is the condition of knowledge. To understand is not to see everything, but to see enough, to connect the pieces, to imagine the whole even when the whole remains out of reach. To ponder the meaning of the Milky Way's size is also to confront scale. 100,000 light years. A million light years if you include the dark matter halo. These are not distances we can experience. They are numbers, abstractions, symbols. We say them, but we do not feel them. The mind cannot hold something so large. It slips away, becomes unreal. And yet the size matters. It tells us that the universe is not small, not intimate, not built on a human scale. It tells us that we are part of something incomprehensibly vast, something that existed long before us and will exist long after. To ponder this is to feel both humbled and awed. Humbled because we are so small, awed because we are part of something so grand. The meaning also lies in connection. The Milky Way is not just a structure in space. It is a system that connects everything within it. The stars are not independent. They orbit together, bound by gravity, moving in patterns shaped by the galaxy's mass. The gas clouds that form new stars are recycled from old stars that died. The elements in our bodies were forged in stellar furnaces and scattered across the galaxy. We are connected to all of it, part of a cycle that spans billions of years. To ponder this connection is to see life differently. We are not separate from the universe. We are made from it. The Milky Way is not something outside us. It is something we are part of, something we carry within us. The carbon in our cells, the calcium in our bones, these are pieces of the galaxy itself. To live is to be a temporary arrangement of galactic matter, conscious for a brief moment before returning to the cycle. The meaning also lies in perspective. From Earth, the Milky Way appears as a faint band of light, easy to overlook, often invisible behind city lights. But from a distance, it would appear as a grand spiral, glowing against the black. Both views are real. Both are the Milky Way. The meaning is that reality depends on where you stand, how you look, what tools you use. This is a reminder that truth is not single but layered. The Milky Way is 100,000 light years across. It is also 300,000. It is also a million. All of these are true, depending on what you measure. To ponder the meaning is to accept that complexity, to resist the urge for simple answers, to embrace the richness of a reality that refuses to be reduced. The meaning also lies in time. The Milky Way is ancient. It formed over 13 billion years ago, in the aftermath of the Big Bang. Stars have been born and died, generations passing, the galaxy evolving slowly. We live in one brief moment of that history. To ponder this is to see ourselves as part of a story far larger than our own lives, far larger than human civilization. And yet, we are the ones who know the story. The Milky Way does not know itself. It has no awareness, no consciousness. It simply exists, turning slowly through space. But we, tiny though we are, can observe it, measure it, understand it. To ponder the meaning is to realize that consciousness matters. Size is not everything. Awareness counts for something. The meaning of living inside something so large also lies in mystery. For all we have learned, the Milky Way still holds secrets. The nature of dark matter, the details of the galactic center, the full history of its formation, the future of its merger with Andromeda. These are questions still unanswered, mysteries still waiting. To ponder the meaning is to accept that we do not know everything, that the galaxy will always hold more than we can grasp. But that is not a reason for despair. It is a reason for wonder. The Milky Way, vast and ancient, is also an invitation to look up, to ask questions, to seek understanding. To live inside it is to live inside a mystery that we can explore, a structure we can study, a home we can learn to know. That is the meaning. Not certainty, but possibility. Not complete knowledge, but the journey toward it. The Milky Way will endure, long after the last human voice falls silent, long after Earth itself is gone. The galaxy will continue. Stars will form and die. The spiral arms will turn. The slow processes of cosmic evolution will unfold, indifferent to whether anyone is watching. This is the legacy. Not just what we have learned about the Milky Way, but the fact that we learned it at all. Humanity, brief and small, managed to measure the galaxy, to map its structure, to understand its place in the universe. That achievement will not disappear, even if we do. The knowledge is part of the cosmos now, woven into the story of how matter became aware of itself. The legacy is also in the questions we leave behind. We have answered some. How big is the Milky Way? Where are we within it? What is it made of? But others remain. What is dark matter? How did the spiral structure form? Are we alone in the galaxy? Or is life common? These questions will outlast us, waiting for future minds to address. The legacy includes the tools we built, the telescopes, the instruments, the methods of observation and calculation. Each generation improved on the last, seeing farther, measuring more precisely, uncovering new layers of the galaxy. This progression is a gift, a foundation on which others can build. The legacy is not just knowledge, but the means to gain more knowledge. But the legacy is also personal. Every person who has looked up at the Milky Way and wondered, every child who asked how far the stars are, every astronomer who spent a lifetime chasing answers, they are part of the story. The legacy is human curiosity, the drive to understand, the refusal to accept mystery without question. And now, as this journey through the galaxy comes to an end, it is time to return. Not to leave the Milky Way, that is impossible, but to return to the immediacy of the present, to the night sky above, to the quiet awareness of being here, now, inside the galaxy. The return begins with a breath, a slow, deep breath, filling the lungs, then releasing. The galaxy is vast, but you are here. The stars are countless, but you see only a few. The Milky Way stretches 100,000 light years, but you are on this planet, in this moment, grounded and present. Look up, if you can. See the band of light, faint or bright depending on where you are. Know that it is not a cloud, not a myth, but the edge of your home. You are inside it. You have always been inside it, and you always will be. The return is also a letting go. You cannot hold the entire galaxy in your mind. You cannot grasp the full 100,000 light years, the billions of stars, the dark matter halo. Let it go. Let it be vast. Let it remain partly unknowable. That is its nature. What remains is the simple fact of being here. You are part of the Milky Way. Your atoms came from its stars. Your planet orbits one of its suns. Your history, your life, your thoughts, all of it unfolds within the galaxy's embrace. The return is to that simple truth. You belong here. The legacy of the Milky Way is not just in the numbers or the discoveries. It is in the sense of wonder it inspires, the questions it provokes, the perspective it offers. To know that we live in a galaxy is to see ourselves differently, to understand that we are part of something larger, something ancient, something enduring. And as the story closes, the tone softens. The galaxy fades into the background. The stars remain, but they become familiar again. Not measurements, but lights. Not data, but beauty. The return is to the quiet of the night, to the stillness of the moment, to the gentle awareness that you do not need to understand everything to appreciate it. The Milky Way will be here tomorrow, and the day after, and for billions of years beyond that. It does not demand your attention. It does not require your understanding. It simply is, vast and patient, turning slowly through space. You can rest now. You have travelled through the galaxy, from its ancient beginning to its distant future, from its crowded core to its invisible halo. You have seen its structure, pondered its meaning, felt its scale. That is enough. The return is complete. You are back where you started, on a small planet, under a dark sky, looking up at the stars. But you see them differently now, not as distant points, but as neighbours. Not as decorations, but as parts of a system. Not as mysteries, but as a home. The Milky Way is 100,000 light-years across. It is vast, ancient, complex, mostly invisible. It holds billions of stars, trillions of planets, mysteries we have not yet begun to solve. It is our home, and we are part of it. And that is the legacy. The knowledge, yes, but also the wonder, the curiosity, the sense of connection, the quiet understanding that we live inside something far larger than ourselves, something that existed long before us and will exist long after, something that we can study and measure and appreciate, even if we can never fully grasp it. The Milky Way endures, and so does the journey of understanding it. That journey is not finished. It will continue as long as there are minds to wonder, eyes to observe, and the will to ask how big, really, is the Milky Way. For now, rest, breathe, and know that you are home, here, inside the galaxy, under the stars,